Hi friends, today we discuss about the concept related on longitudinal chromatic aberration. First of all, the question: find an expression for longitudinal chromatic aberration for an object at a infinity distance and an object at a finite distance. Let's learn about this topic. What is longitudinal chromatic aberration? Longitudinal chromatic aberration occurs when different colors of light focus at different distances along the optical axis of a lens. This means that even if the lens is focused for one color, other colors will be slightly out of focus, leading to color fringing or blurriness in the image, particularly around high contrast edges. Example: imagine a white light source passing through a lens. Blue light might focus closer to the lens, while red light focuses further away. This difference in focus for different colors is longitudinal chromatic aberration. Now we will derive expressions for both cases. When the object is situated at a infinity distance. So, to derive the relation for longitudinal chromatic aberration of a thin lens when the object is situated at infinity. When an object is placed at infinity, the light rays entering the lens are parallel because the lens bends different colors of light differently. They come to focus at different point along the optical axis. When the object is at infinity, longitudinal chromatic aberration is the difference between the focal lengths of red and violet light. It shows how much the image shifts along the optical axis due to wavelength dependent focusing. The fundamental lens maker's formula states that the focal length f of a lens for an object at infinity is given by 1 by f, that equals to mu minus 1 into 1 by r1 minus 1 by r2, where mu is the refractive index. R1 and R2 are the radius of curvature of the lens surfaces. Define focal lengths for different colors. Due to chromatic dispersion, refractive index varies with wavelength. So define FV, FR, and FY represents the focal lengths for violet, red, and yellow light. Mu V, mu R, and mu Y represents the refractive indices for violet, red, and yellow light. Using the lens maker's formula, applying to different colors. For violet light, 1 by FV, that equals to mu V minus 1 into 1 by R1 minus 1 by R2. This is the equation number 1, where FV represents the focal length for violet light. Mu V represents the refractive index for violet light. R1 and R2 are the radius of curvature of the lens surfaces. For red light, 1 by FR, that equals to mu R minus 1 into 1 by R1 minus 1 by R2. This is the equation number 2, where FR represents the focal length for red light. Mu R represents the refractive index for red light. R1 and R2 are the radius of curvature of the lens surfaces. For yellow light, 1 by Fy, that equals to mu y minus 1 into 1 by R1 minus 1 by R2. This is the equation number 3, where Fy represents the focal length for yellow light. Mu y represents the refractive index for yellow light. R1 and R2 are the radius of curvature of the lens surfaces. Subtract equation 2 from equation 1. To find the difference in focal lengths due to color means chromatic aberration. 1 by Fv minus 1 by Fr, that equals to mu V minus 1 into 1 by R1 minus 1 by R2 minus mu R minus 1 into 1 by R1 minus 1 by R2. Factoring out common terms. Since the term 1 by R1 minus 1 by R2 is common to both parts of the right hand side, it can be factored out. 1 by Fv minus 1 by Fr, that equals to mu v minus 1 minus mu r minus 1 into 1 by R1 minus 1 by R2. Simplifying the refractive index terms. Expand the terms within the first parenthesis. 1 by Fv minus 1 by Fr, that equals to mu v minus 1 minus mu r plus 1 into 1 by R1 minus 1 by R2. The constants minus 1 and plus 1 cancel out, leading to the simplified expression. We get 1 by Fv minus 1 by Fr, that equals to mu v minus mu r into 1 by R1 minus 1 by R2. This is the equation number 4. Multiply and divide by mu y minus 1. We know multiply and divide the right hand side of equation 4 by mu y minus 1 and rearrange the left hand side to this form. We get Fr minus Fv by Fv Fr, that equals to mu v minus mu r by mu minus 1 into mu y minus 1 into 1 by R1 minus 1 by R2. This is the equation number 5. Using the lens maker's formula, applying to the yellow color, mu y minus 1 into 1 by R1 minus 1 by R2, that equals to 1 by Fy. This is the equation number 6, where Fy represents the focal length for yellow light. Mu y represents the refractive index for yellow light. R1 and R2 are the radius of curvature of the lens surfaces. This equation seems to be a specific case or approximation, possibly related to the mean focal length or a condition for achromatic combination, where the product of the focal lengths of violet and red light is approximately equal to the square of the focal length of yellow light. That FV FR that equals to Fy square. This is the equation number 7. Substituting equation 6 and 7 into equation 5 leads to this expression, which relates the difference in focal lengths to the refractive indices and the mean focal length. It means in fifth equation, left hand side FVFR term replace with Fy square. Right hand side mu y minus 1 by R1 minus 1 by R2 term replace with 1 by Fy. So finally we get Fr minus Fv by Fy square that equals to mu v minus mu r by mu y minus 1 into 1 by Fy. This is the equation number 8. This is a standard definition of dispersive power of the lens material. Omega equals to mu v minus mu r by mu y minus 1. This is the equation number 9, where omega represents the dispersive power of the lens. From 8 and 9 equations, it means substitute omega value into equation number 8. We get Fr minus Fv by Fy square that equals to omega into 1 by Fy. Simplify the equation. On the left hand side, the denominator Fy square, and on the right hand side, denominator Fy cancelled out. Remaining term Fy in left hand side denominator. Finally, we get Fr minus Fv by Fy that equals to omega. Rearranging the above equation, it means on the left hand side denominator Fy converts to the right hand side, means omega into Fy. Finally, we get Fr minus Fv that equals to omega Fy. This is the equation number 10, where Fr minus Fv represents the distance between the focal points of red and violet rays. Fy represents the focal length for yellow light, that is mean focal length. Omega represents the dispersive power of lens material. The conclusion: the longitudinal chromatic aberration for a thin lens for an object at infinity is equal to the product of its mean focal length and dispersive power of its lens material. This means that if you multiply the mean focal length of the lens by the dispersive power, you will get the longitudinal chromatic aberration. Let's go through the derivation step by step for longitudinal chromatic aberration when the object is situated at a finite distance. The basic lens formula in optics establishes a relationship between the focal length f, object distance u, and image distance v of a lens. It is mathematically expressed as 1 by v minus 1 by u that equals to 1 by f. The basic lens formula is applied for violet and red light. For violet light, 1 by Vv minus 1 by u that equals to 1 by Fv. This is the equation number 1. For red light, 1 by Vr minus 1 by u that equals to 1 by Fr. This is the equation number 2. Since chromatic aberration is due to different wavelengths, means colors focusing at different points. Subtracting equation 2 from equation 1, we get 1 by Vv minus 1 by u minus 1 by Vr minus 1 by u that equals to 1 by Fv minus 1 by Fr. Expansion of the above equation. 1 by Vv minus 1 by u minus 1 by Vr minus into minus plus. So, plus 1 by u that equals to 1 by Fv minus 1 by Fr. Finally, we get 1 by VV minus 1 by U minus 1 by VR plus 1 by U that equals to 1 by FV minus 1 by FR. Cancelled out minus 1 by U and plus 1 by U. Finally, we get 1 by VV minus 1 by VR that equals to 1 by FV minus 1 by FR. Take LCM on both sides. We get VR minus VV by VV VR that equals to FR minus FV by FV FR. This is the equation number 3. It is assumed that VV VR that equals to Vy square. This is the equation number 4, where Vy is the image distance for yellow light, that is mean image distance. Similarly, it is assumed that FV/FR that equals to Fy square. This is the equation number 5, where Fy is the focal length per yellow light, that is mean focal length. From 3, 4 and 5 equations, it means substituting equations 4 and 5 into equation 3. Simply VVVR replace with Vy square and FVFR replace with Fy square. We get VR minus VV by Vy square that equals to FR minus FV by Fy square. Rearranging to find the longitudinal chromatic aberration VR minus VV. It means on the left hand side, the denominator Vy square converts the right hand side. So we get VR minus VV that equals to FR minus FV by Fy square into Vy square. This is the equation number 6. From optics theory, focal length difference is related to dispersive power omega given by omega that equals to Fr minus Fv by Fy square. Fr minus Fv that equals to omega Fy. This is the equation number 7. This equation introduces the dispersive power omega of the lens, which quantifies how much the lens disperses different colors of light. Substituting equation 7 into equation 6. It means in equation 6, Fr minus Fv replace with omega Fy. So we get Vr minus Vv that equals to omega Fy by Fy square into Vy square. On the right hand side, the numerator Fy and the denominator Fy square cancelled. Remaining term, the denominator Fy. Finally, we get Vr minus Vv that equals to omega by Fy into Vy square. Rearranging to find the longitudinal chromatic aberration. We get Vr minus Vv that equals to omega Vy square by Fy. The conclusion: this equation shows that longitudinal chromatic aberration Vr minus Vv depends upon the dispersive power of the lens omega, the mean focal length of the lens Fy, and the square of the image distance for mean light Vy square. This is our brief explanation of longitudinal chromatic aberration for an object at a finite and infinity distance. Thank you very much. Padmam Himam.